In order to best understand these two concepts of electric field strength and electric potential, specifically for uniform fields in this case, we're going to go back and we're going to take a look at gravitational field strength and gravitational potential because there's very easy connections between the two. So you don't necessarily have to worry about all of this. This is information we've looked at before. However, just remember that if we're talking about a classroom, there's a gravitational field which points down. And when we say gravitational potential, which we've represented with GP, that's the amount of potential energy a mass will possess per kilogram when it's placed at a given location. So hopefully this is starting to jog your memory. And the gravitational field strength is the amount of force a mass will experience per kilogram when placed at a given location. So these two, gravitational potential and gravitational field strength, those are the two that are not a property of the object. Those are properties of like the field or the space around like a planet or an object that has mass. So if you remember these, it's going to be significantly easier trying to understand these two concepts. So really quickly, if we just take a look at the math, and you don't have to be overly concerned with how these are derived, but the gravitational potential is essentially the amount of energy, gravitational potential energy, per kilogram of mass that the object will have. So if I just replace Eg with mgh, the m's cancel, and you get lowercase g times h. Again, this is an equation that we've really ever used, but the important thing to realize is that the gravitational potential is just the gravitational field strength times how high above some reference point you are, usually the ground in this case. And for gravitational field strength, well, it's the amount of force per mass, and we know that force equals mass times acceleration. The masses will cancel, and that's why we've generally called little g the acceleration due to gravity. So in that case, the acceleration due to gravity, the field strength, it's all the same. All right, but the one thing I'd like to get across is that potential is the amount of energy per mass, and the field strength is the amount of force per mass. These are not new topics. Hopefully you guys are remembering these. So how does all of this apply to electrical fields and concepts like electric potential and electric field strength? Well, if you take a look at this definition, you should notice there's only some minor changes. Just like I have two plates, a positive and a negative, I have an electric field that points down because field lines always show the direction that a positive charge will experience a force in, and a positive charge will be repelled by this plate and attracted by this plate. Well, if you remember up top, gravitational potential is the amount of potential energy a mass will have per kilogram when placed in a gravitational field. If we look at the definition of electric potential, it's the amount of potential energy, which so far is the same definition, a charge, okay, so we're talking about charges instead of masses, will possess when placed at a given location. Hopefully, as you look at this definition, you see it's the same exact definition. However, we're talking about charges instead of masses. And because we're talking about charges, we're not talking about per kilogram. We're talking about per coulomb, because that's what we measure charges in. So the electric potential, which we usually represent with a capital V, because it really stands for voltage, which we'll get to in more detail later. The electric potential is really the amount of potential energy a charge will possess per coulomb when placed at a given location in a field. So it's no different than the gravitational potential, except we're not talking about masses, we're talking about charges. That is it. Definition is exactly the same other than the charge and the fact that we use the unit of charge. Electric field strength, same thing. Well, gravitational field strength, the force that a mass will experience per kilogram when placed in a gravitational field. So the electric field strength is quite simply the amount of force, still force, the amount of force a charge will experience per coulomb when placed at a given location in an electric field. So the concepts are identical, but again, we're just talking about charge instead of mass. That's the only difference between these two. So if we take a look at like some of this math, but now this math applies a little bit more usefully, we know that the electric potential is just the amount of electrical potential energy per unit of charge. And we know from previous lessons that the electric potential energy is QED. Just like for gravitational potential energy, it's mass times the gravitational field times the height above some reference point. In this case, it's just the charge times the electric field strength times the distance above a certain reference point. So again, it's the amount of electric potential energy per unit of charge. Those two charges, the two Q's, will cancel, and you wind up with just the field strength times the distance or the height above some reference point. So if we take a look really quickly, electric potential is the electric field strength times the height above a reference point, whereas the gravitational potential was the gravitational field strength times some height or distance above a reference point. So again, it's no different. We're literally just talking about gravitational fields as opposed to electrical fields. All right, so electric potential, it's still measured in the same units for the most part. It's still energy per charge, so joules per coulomb. Gravitational potential, joules per kilogram. Electric potential, joules per coulomb. Same for field strength. Electric field strength, newtons per coulomb. Gravitational field strength, newtons per kilogram. So we're just swapping out the mass for a charge. And of course, the distance is measured in meters. So just to give you a quick example, I have an electric field. I'm given that the field strength is 10 newtons per coulomb. So for every coulomb of charge I place in this field, for every 1 coulomb, I'll get 10 newtons of force. I have two locations. Location A, which is 3 meters above my reference point, which I've chosen to be this bottom plate, and point B, which is this elevation, which is 2 meters above the reference point. So if I want to know what the electric potential at any point along region A here is, well, we know that it's going to be the electric field strength times the distance above my reference. So 10 times 3 is going to give me 30. For any charge that I place on this line, I will get 30 joules per coulomb. Place 1 coulomb of charge, I get 30 joules. I place 2 coulombs of charge, 60 joules, and so on and so forth. Now, line B is closer to the negative charge, the negative plate. Now, a charge that's positive will want to be closer to that, and when objects move to areas they want to be, they'll lose energy. If you remember back when we talked about electric potential energy. So any charge I place on line B should have less energy because it's closer to where it wants to be. If I want to double check that, well, the electric potential at line B is going to be the field strength times the distance above. Same field strength, it's a uniform field. The height is 2 meters, or the distance is 2 meters, so I get 20 joules per coulomb. And it makes sense when you think about it. If this was a classroom and we're talking about gravitational fields, well, if you want something to have the most gravitational potential energy, hold it up near the ceiling. It does not want to be there. So in this case, when we're talking about positive charges, because we always use like positive test charges, they do not want to be up here. So just like holding a mass near the ceiling will give it the most energy or the most gravitational potential, holding a positive charge closest to the positive plate will give it the highest potential energy as well as the highest electric potential. The only other concept, and this one is significantly easier, is the electric field strength. We know that field strength is generally the force you will get per unit of whatever in a given location. So electric field strength is the electric force per unit of charge. If we rearrange that really quickly, you'll actually find that it's just a rearrangement of the original electric force equation. So there's not much more to this. If you'd like to know the field strength, place a charge in the field and measure the force on it. So to show you an example, here I have some unknown field. I don't know what the strength of it is, but I have a 2 coulomb charge that I've placed right here, just 2 meters above my reference point, and I measure that it experiences 300 newtons of force pulling down. Well, if I know the force and I know the charge, I can therefore determine the electric field strength. This field must have a field strength of 150 newtons per coulomb, and I need to have a direction, downward in this case. If I place a charge anywhere in this field, for every 1 coulomb of charge, it will experience 150 newtons of force directed down. So the big takeaway, as you take a look at these two concepts, they are no different conceptually than everything we've looked at regarding gravitation. However, anywhere you've seen mass, you're going to use a charge now, and anywhere you've seen kilogram, you're now going to use coulomb.